All right, so in the interest of time, I think we should get started so that everybody has a fair amount of time to speak. So thank you all for coming this evening or whatever time of day it is for you. We're excited to talk to you today about fractions and algebra and the connections between these important parts of math knowledge. And so we're going to hear from a cool set of speakers today with each with kind of a different approach to this question. So first, we're going to hear from Dr. Julie Booth talking about an experiment looking at the connections between these. And then we're going to hear from Kellyanne Gesuelli, who's going to talk about some connections, again, longitudinally between these types of knowledge. And then Tori J is going to present kind of some theory and plan for a study that has yet to be conducted. And then I'm going to end with some questions that I want to leave you all thinking about as we leave. So with that, we're going to start with Dr. Julie Booth. So you can share your slides and begin whenever you're ready.
Hi, everyone. Thanks for joining us this evening. I know it's kind of an odd time for a symposium, but you know, we'll think of it as a little bit of a nightcap for those of us, at least on the East Coast. This project that I'm going to tell you about is part of a larger grant that I have with Christina Barbieri, Laura Young, and Christy Newton, called Opening the Door to Algebra, looking at connections between fraction knowledge and algebra learning. If you go back a little bit in time, and maybe this will let me advance. There we go. In 2008, the National Mathematics Advisory Panel put out a lot of findings about what was important in mathematics. And one of the things that they asserted was that a knowledge of rational numbers, including fractions, was one of the most important types of knowledge for algebra learning. The interesting thing was that they gathered that from talking, you know, doing a lot of interviews and talking with teachers, talking with scholars, but there wasn't actually any empirical research to show that fractions were impactful in algebra. So all of that empirical evidence that we now know about has begun to amass only over the last decade. In my lab in particular, we have done work to show that students' knowledge about fractions is predictive of their algebra readiness, and then also of their performance and learning in algebra once they are learning about it. What hadn't been done is any kind of experiment to determine whether the relationship between fractions and algebra is causal. So our question broadly was, would intervening to improve students' fraction knowledge increase their ability to learn algebra? So just a little bit of background in terms of thinking about intervening on fraction knowledge. There are a number of different types of things about fractions that someone could know: how to add, subtract, multiply, or divide the fractions, how big the fractions are, how big fractions are compared to each other. In this particular project, we're looking at two types of fraction knowledge: knowledge of magnitudes of fractions, which is the relative sizes of fractions and within the scale of 0 to 1, and fraction computation. So that's the ability to add, subtract, multiply, or divide fractions. And we use an intervention strategy that we call the by example approach. This is something that I've developed over the last decade or so with a strategic education research partnership, where within practice sessions in mathematics, we replace some of the practice problems that students would just solve on their own with a correct or incorrect example for them to instead study and explain. So our research questions for this experimental study were: are fraction magnitude or fraction computational skills causally related to algebra learning? That is, does explaining examples about fraction computation improve students' algebra learning? Or does also explaining examples about fraction magnitudes improve algebra learning? We were trying to think strategically about the number of conditions that we could conceivably pull off in a within classroom, because this is a within classroom design. And so both of the experimental conditions did get fraction computation examples, but only one of those groups got fraction magnitude examples. The participants in this study were 130 eighth grade students across 23 different classrooms in the US. 51% of the students were male, And you can see the ethnic breakdown. The students were randomly assigned within classroom to one of three conditions. So the control kids, the kids that were randomly assigned to the control condition, got 32 sets of problem-solving items, some of them computation, some of them magnitude related. For the computational examples condition, they got 20 sets of example and problem pairs in the style of by example, all based on computation of fractions. And then for the magnitude items, they got all 12 sets of problem-solving items that the control group had gotten. And then finally, in the third group, they got example problem pairs for both computation and magnitude. The intervention materials included these kinds of examples, and I just wanted to show you sort of, so you can see that the computation examples on the left indicate a correct or incorrect solution for some sort of addition, subtraction, multiplication, or division problem involving fractions, where it's clearly marked that the fictitious student did the arithmetic correctly or incorrectly. And there are self-explanation prompts guiding the real student's thinking when trying to make sense of what's going on in the example and what makes the shown procedure correct or incorrect. And then we do the same thing for the magnitude examples, where they're shown examples of students correctly or incorrectly placing numbers in relative fashion on number lines or relative to each other, and then explaining why that procedure or thinking process that the fictitious student used is correct or incorrect. The design of the study was pre-test, which was given at the start of the year, intervention, these materials that were given throughout the school year at times deemed appropriate by the teachers. So if the teacher was reviewing fractions at a particular point in time, they could choose to use some of the worksheets then, or they could sprinkle them across multiple months, however they felt it would be best used in their classroom. At the very end of the year, then they took a post-test, and at pre and post-test, it was a paper and pencil test of all of the fraction and algebra measures, which I'll show you on the next slide. But as I mentioned, all of the measures in the intervention materials were given during students' math classes by their teacher as part of their regular class activities and incorporated into those activities when the teacher deemed it to be most appropriate. The fraction measures that we gave were looking at students' skill with fraction computation. So again, adding, subtracting, multiplying, dividing fractions. And their skill with placing the different fractions on a number line. So where would 3/11ths go on a number line that has 0 at the left end and 1 at the right? For algebra, we looked at two key measures. Their feature knowledge, which we define basically as their understanding, conceptual understanding of the particular features in a problem. So you can see that some of the items may have targeted the equal sign, some targeted sort of principles of number and addition, subtraction, multiplication, division, sort of commutative properties, distributive properties, etc. And then we looked at their skill at solving algebraic procedural problems, which took the form of either equations or word problems that were in similar in structure to the same level of equations that they would be asked to solve. So what we found, this is a complex overarching model, but I want to draw your attention to two things. One, that the computational examples plus magnitude problem solving. So the condition where they explained examples about the fraction computation, but then just did practice problems for magnitude. Those students did learn more about algebra over the course of the year. Remember, we weren't teaching them algebra. We were having them practice fractions. They were learning the algebraic content over the course of the year. So students in that group who got computational examples only did improve their learning of algebra over the course of the year. One other thing I want to point out, however, is that the magnitude of plus computational examples condition, there was a main effect of condition there on algebraic procedures, but it's in the opposite direction. The control group performed better, learned more about algebraic procedures by the end of the year than the students who had had both magnitude and computation examples. So the interesting thing here is that, first of all, we have our first causal evidence of fraction computation impacting algebra learning. Improving the students' fraction computation using the by example approach actually led to them learning more from the instruction they were already getting in the classroom about algebra. Having students explain the worked examples of fraction computation problems does yield improvements in algebraic feature knowledge over the course of the school year. But having students also explain worked examples of fraction magnitude problems doesn't aid in learning algebra feature knowledge and might actually harm their learning of algebraic procedures. This is something that we find really interesting, given that some of that earlier work that I talked about briefly at the beginning shows that fraction magnitude knowledge is one of the bigger predictors of algebra learning over time. So there's something interesting going on here in that it matters whether they have good fraction magnitude knowledge, but trying to take the time in 8th grade to improve it is not necessarily a good use of their time if your overall goal is to try to improve their algebra learning. This work suggests, though, that taking the time out during the year to study and improve their fraction computation knowledge can actually lead to more benefits to their algebra learning over the course of the year. In work that we are continuing to do, we want to look at how these patterns look for younger students. So for example, while it might not make sense to take the time to try to improve students' magnitude knowledge of fractions in 8th grade, maybe for 7th graders, maybe for 6th graders, it is a good use of time. That is something that we still don't know. What we have here is that even as late as 8th grade, taking the time to improve students' fraction computation knowledge improves the amount of learning that they are able to achieve from their standard algebra instruction. And this just is to acknowledge the funding from the US Department of Education Institute of Education Sciences. Alex, I'm not sure if we're doing questions right away or if you want to wait to the end.
Yeah, I think it'd be great to take a few questions here if we have some. Excellent job, thanks. So you can feel free to unmute and ask a question or post a question in the chat if you have one.
Can I ask a question, Alex?
Yes,
thank you, Julie. I was just wondering, could it be, you know, you found these differences for fraction computation versus magnitude. Could it have something to do with the these different content areas or different aspects of fractions interacting differently with the worked examples versus the things the control students were doing? Like, could it be that looking at worked examples is just more beneficial in the arena of fraction computation than it is with fraction magnitude?
No, absolutely, a good question. What I didn't present here is the work showing what working with these worked examples did for the students' actual fraction magnitude or fraction computation skills. And what we do when we do find there that the magnitude examples improved their knowledge of fraction magnitudes. So I think it has something more to do with the fact that they've gotten to this point in time in their education and they still don't understand the magnitudes of fractions. It's still malleable, but it's taking time away from some of the other content that they need to learn. And I think that if intervention is going to have an impact in that way, it's going to have to be earlier. There must be some threshold that they need to reach before this point to be able to benefit from the algebra instruction in the same way.
I think we have time for maybe one more question if there is one. And Kellyanne, maybe you can get set up as we're taking another question. Julie, if nobody else has a question, I'd love to hear a little bit more about what you think the mechanism might be. Like, what do you think that these kids who are getting the computation worked examples are sort of getting or interacting differently with in their algebra instruction? Or what do you think? I'm sure like it's hard to know exactly what's going on, but what do you think?
Of course. No, I think that what is going on is that the way that we design examples in the by example approach, we are really gearing the students' attention towards particular features of the problem that they might not normally interpret correctly. And so I think that some of that is, the mechanisms could be twofold. So one, if we're improving the students' fraction, their conceptual understanding of the fractions themselves, that they likely don't have to spend as much time on that whenever they are working in algebraic equations, because solving algebraic equations always includes, it's going to include fractions one way or another, either in the initial problem or once you start dividing things, et cetera. But what we didn't find in this particular study was an improvement in their solving of algebraic equations. It was in their ability to understand the features of the algebraic equations. And so I think that again, they might be, if they already understand the fractions, then whenever other features of the problems are being explained in class, they may be able to devote more attention to that. But I think that there may also be something in the structure of the equations. I think that there are enough similarities between the structure of equations and the structure of these fraction arithmetic problems, that if they're getting something about how different parts relate to each other in the fraction problems, that some of that is helping them understand how different pieces of the algebraic equations relate to each other when they're learning about the algebraic equations over the course of the year.
Sure, awesome, thank you. Okay, Kellyanne, if you want to go ahead and get started.
Yeah, no, that's actually a great segue for what we actually think is going on similarly too at the end product of our study that also involved Dr. Booth as well. So I looked at transitions in algebra problem representations, specifically looking at middle schoolers' development in encoding of equations. If it lets me, let's see. Okay, so just some background. We know that algebra, right, it's a difficult area of mathematics for many students, and encoding is a critical but understudied skill necessary for solving these equations and higher math skills. So what's encoding? We throw the term around a lot, but what does it actually mean? This is when you break down important problem features in a way that's able to be perceptually processed in a way that's understandable to that problem solver, to the student. We know encoding accuracy is a significant predictor of a variety of students' math skills, including algebraic feature knowledge. So how do we measure encoding skills? Typically, we use a reconstruction task, and this involves showing an algebraic equation briefly on a screen. It then disappears from sight, and the student is asked to recreate it from memory. So here's an example of one student who solved the equation correctly. Not solved it, I'm sorry, represented it correctly, and the other student who encoded it incorrectly. So encoding really is that first step in representing or storing that information from your memory, but it's more than a memory task, right? It's showing us how the student is relating different features of the problem, what they're even attending to, and their overall understanding of the equation. So here to us, we see the student made an error. They had two equal signs. So for us as adults who've had background knowledge and experience with algebra, that would tip us off, hey, maybe something's wrong. Maybe I made a mistake here. I should go back. But for a middle school student who's first learning this, and especially if they're struggling, that might not raise a red flag, but that tells us something, right? Where those misconceptions are, where those areas of difficulty lie. So research that does focus on encoding skills typically looks at these mean aggregate errors. So rather than looking at different subtypes that just tell us the average number of errors, they also report group means for the students. So that just tells us how the average student is performing. So conversely, we know very little about individual variability of these skills, as well as predictors that influence the development of encoding and other characteristics that influence different learning pathways. And past research has shown that fraction magnitude predicts improvements in encoding accuracy, but it remains unclear when we have multiple measures kind of in models, whether it still remains a significant predictor of encoding skills. So our research, we take a person-centered approach to examine the individual differences in middle school students' representation of different problem features in algebraic equations at the start and end of a school year. So we have this longitudinal piece here. And we use what's known as latent profile analysis, which I'll go into later, but we're basing these profiles based on students' encoding errors that they make. Then we determine the likelihood that students' encoding skills change or remain the same over the course of that school year using what's known as latent transition analysis. And then finally, looking at whether fraction magnitude or other skills produce or predict these differential pathways. And we use multinomial logistic regression for that. So our study involved 306 middle school students from the Northeast United States. We had 59.2% females. This was a cross-sectional study, so we had 6th, 7th, and 8th graders in terms of, we didn't follow from 6th to 8th grade, but we had those grade levels represented. We also had a sizable number of students who received free and reduced lunch, as well as students from minority and underrepresented backgrounds. So for the procedure, we had students complete 2 paper and pencil tasks. One involved assessment of their algebra knowledge at the start and end of that school year, and then an assessment of various fraction skills, namely their magnitude understanding with fraction number line estimation and fraction arithmetic. And then in between the 2 time points, students received business as usual classroom math instruction. So for those measures for fraction magnitude, we did the traditional fraction number line estimation task, and their performance was based on their mean percent absolute error. So actually here a lower PAE means they're more accurate. And then for fraction arithmetic, they were asked to solve a variety of symbolic fraction equations with a variety of different operations. And then finally, for that encoding of equations, we used that reconstruction task I showed you earlier, and we asked them to do that for 6 different equations. So just to back up, so that first LPA piece, basically we said we're looking at these encoding errors. So we looked at a variety of ones. So representation of the equal sign, addition, subtraction, negative symbols, the variable, right? If it says 2p and the student put 2w, representation of the numbers in that equation, and then representing fractions. So what latent profile analysis is, in a nutshell, is seeing, do we have an overall homogeneous population or underlying heterogeneous groups that are similar to each other in a certain way, but different than the others. So each latent profile, the students within it are as similar to each other as possible and as different from those in the other group. And so with our data, we found that a 2-profile solution fit best based on a number of fit statistics and model interpretability. And what we saw is we had 1 profile with low encoding errors across the different subgroups that or subtypes that we looked at. And this was for 46.7% of the population. And then 53.3% had an overall high amount of errors for the different subtypes. So then we move on and again did this for the end of the year. We again retained a 2-profile solution that was represented by a low encoding error profile and a high encoding error profile. But we see now that we have 65.4% of the students in the low encoding error profile and 34.6%. So those proportions are changing. So how do we know? Does student who starts here, are they still the same student here? That's what we used latent transition analysis for. This big path diagram won't go too much in depth, but basically we have our dependent variables here, right, which are the different encoding errors that are used to inform our latent construct, which is our encoding error latent profile at the start of the year, and then we do this again at the end of the year. And then we see of the students who start in one profile, their probability to stay the same or change, and what the impact different covariates such as fractions and grade level have on those differential transitions. Then moving into the results for that, we see students who are consistently low, so those who start with low encoding errors, have a 0.6 probability of remaining in that error profile at time 2. Alternatively, for students who have increasing errors, we see those who start with low encoding errors only have a 0.38 probability of transitioning to that high encoding error profile. And that's only about 10% of our population, which we expect, right? We don't expect a lot of students to increase their errors with additional instruction in math in general. Then we have the students who are consistently high. Those who started high had a 0.5 probability of remaining high. But then most interestingly, at least to me, is more of these productive shifts, right? Students who start with high errors also had a 0.5 probability of transitioning to this low encoding error profile. And we saw this for about 36% of our students. And so this kind of productive shift is suggesting, learning, improvement in these skills. So these skills are malleable is basically what this is telling us, which yeah, is good. So what predicts these transitions? So using multinomial logistic regression, right? We have those covariates where kind of those arrows going in at the bottom of the path diagram. We see that of students who start with high encoding errors, so students in 7th and 8th grade with high encoding errors were more likely to transition to a low encoding error profile than their 6th grade peers in that study. And then additionally, students, who struggle in the beginning, higher error profile, with better fraction arithmetic skill were more likely to transition to a low encoding error profile. Additionally, though, we did not see fraction magnitude predicting any improvements in these skills or this specific transition from high to low encoding errors. So in conclusion, we see there's a large amount of variability in the developmental trajectories of middle school students' equation encoding. We see considerable change occurs over the course of the school year for each of those grades that we examined, and 7th and 8th graders were more likely to improve in their encoding skills than 6th graders, and strong fraction arithmetic skills predicted improvements in encoding accuracy, whereas fraction magnitude knowledge did. Okay, so why? This gets back to what Julie was kind of explaining earlier. Why might fraction arithmetic predict transitions from less to more optimal encoding profiles over the course of the year, right? So this idea that they're relying on similar forms of thought, I won't restate everything Julie said, but again, really more of this last piece that, right, when we do fraction arithmetic or when students do fraction arithmetic, they have to understand that relationship between the numerator and denominator simultaneously while they're looking at it, manipulating it, right, finding a common denominator. And that's similar, like if we go back to an equation or a more complicated algebraic equation, we have y over x, and we have to manipulate them in very similar ways to isolate that variable. So just that underlying understanding of being able to mentally represent kind of these abstract concepts and then manipulate them mentally, kind of relying on similar forms of thought. So I'd like to thank my collaborators and also our funding for the project from the IES. Thank you.
Awesome, thanks, Kellyanne. It looks like David has a question.
Yeah, thank you very much. That was a really interesting talk. My question is a little technical. I guess I'm wondering what we get from the LPA in a case like this, where you just end up with two groups that are kind of high and low. Like it would kind of seem like that's essentially just taking an underlying continuous variable and changing it into a categorical one with two values, which I've always been told is not good. So are we benefiting in any way from the LPA in this particular case? Of course, you didn't know that that would be the result before you did it, but given that that was the result. Right.
So I think here so you're asking if I was doing more of like a regression type piece or?
Well, let's say that instead of taking the profiles as the basis for your analysis, you just counted the total number of encoding errors. That would presumably be more sensitive in terms of differentiating between individuals. So is there any advantage to using the profiles rather than an underlying continuous variable like the total number of errors?
Well, I think because our profiles, I mean, for this case, they weren't staying exactly the same, but we were looking at the different underlying factors here, but getting more at the individual variability and that transition, which I don't know if you could get if you just had a continuous latent variable. I don't know if we would see that transition piece, right, as a continuous variable with it informing, because then we can't get those latent profiles without having it informing the latent construct. And then I can't see exactly those shifts where students are. And like I can find student A, student B, student C, which I don't, if we had a continuous variable and we couldn't use this latent profile piece, we wouldn't be able to do.
So couldn't you just look at end of your number of encoding errors minus start of your encoding errors, and that would be a measure of change, which I think I would say the same thing about that I would say about the profiles themselves, which is like if you look at the transitions, that's basically taking an underlying continuous variable, which is change in the total number of errors, and turning it into a categorical one, which is there are the four possible transitions. So it's four levels, but isn't what we really want to know whether the errors are increasing or decreasing and how much they're increasing or decreasing? And if looking at the transitions, we only answer the first of those two questions. But if we look at the change score, we would answer both of them.
You go with the change score, but I don't know with the change score, and you might be more knowledgeable on this aspect about it. You can't get with those change scores, again, with that average variable, I don't know if you're getting the individual, looking at the individual variance of those students. Can you still do that with the change scores? Look at the individual variation within your population?
I'm not actually at all knowledgeable. That's why I'm asking. I'm sorry, I don't have.
So that's what I like about structural equation modeling with the latent profiles, because I get that looking at that individual variability that often gets masked when we use more kind of average aggregates. So looking at the difference in the breakdowns between these students, getting a more nuanced understanding of it, that again could be lost. Like we could have students who are low and then high, but they might get that masked overall by that mean. And so I'm trying to parse it out more. And it did happen. They were low and high, but I guess the thing is that it didn't. And I get you're saying for this one particularly, but it didn't have to be the same profiles at time 2. It could have been something totally different, and we didn't know that. So, going forward, it happened to be the same. But that's what I think is really cool about this method is it doesn't have to be. It could be 5 profiles, and then looking how it goes. And that would be interesting to further, if it did further break down the line. But this was kind of a simplistic model here for this one, which I do get that. Yeah.
Thank you.
All right, thanks, Kellyanne. I think that we can have Tori get set up here. If there is one more short question, we could take it. Otherwise, hopefully we can get Tori going here. Martha has a question, I think.
Yeah, I just wanted to observe that I think it's actually really interesting that you only got 2 profiles, because you had enough different kinds of encoding errors that one could have imagined that there might be some kids who, for example, only miss negative signs, and other kids who, are not good at recalling the position of the equal sign, but they pay attention to the other things. Or maybe some kids really focus on the numbers or something like that. And so I actually think the fact that you repeatedly found the 2-factor solution is itself kind of interesting. Yeah, I guess I would also, think about whether the things that they're encoding are more similar to what goes on in the fraction arithmetic task. So the fraction arithmetic task also has, operation signs and equal signs and other things like that. Whereas in the magnitude task, they're activating, magnitude knowledge that may not come up at all in the algebra or arithmetic sorts of tasks. And so I think we're seeing an interesting pattern across Julie's study and your study that the magnitude knowledge isn't what's really relevant here. It's experience thinking about and attending to arithmetic sorts of things. So it's not really a question, I guess, but something to observe. So.
Yeah, no, thank you. And with the profile too, even though they are making overall low and high, we can see with the coefficients, which are more highly weighted, which we can look into deeper. But definitely I'd be interested to see if, the relationship and similarities between what they did on that fraction arithmetic task for us and those encoding errors, looking at the correlations between the two. Thank you.
Awesome, thanks. All right, in the interest of time, let's let Tori begin.
Cool. I am super excited to be following these 2 presentations because I'm going to be talking about fraction equivalence's relationship to algebra, primarily in theoretical terms. So this means that we'll really be digging into what might be happening, mechanistically, to be explaining the patterns that the other 2 groups have found happening in fraction arithmetic. So we're in the process of piloting a study now, and we're hoping to launch full data collection soon, but we're not yet at a point where we have results to discuss. Can I move? Okay. So as other speakers have discussed, there are consistent associations between fractions proficiency and algebra proficiency, and we're very interested in understanding the relationship so we can leverage it to improve students' algebra outcomes. And there are many potential mechanisms underlying this relationship, but we're especially interested in potential mechanisms that would involve the transfer of conceptual knowledge or skills and that are teachable in lesson form. And one category of fraction tasks, fraction equivalence, strikes us as a particularly good subset of fraction tasks to consider in this respect. So first, what is fraction equivalence? Fraction equivalence involves making fractions with the same numerical magnitude, but different numerator and denominator components. For example, 1/2, 2/4, and 12/24 are all equivalent fractions. Students might be asked to construct equivalent fractions as a standalone task. For example, they could just be asked to produce fractions that are equivalent to 1/2. And students also use equivalent fractions as a step in solving arithmetic problems. So for example, to solve 1/2 plus 5/6, they might replace 1/2 with 3/6. So we see a few main ways fraction equivalence could be related to algebra proficiency. The first is that fraction equivalence tasks provide experience maintaining numerical relationships. The second is that fraction equivalence provides experience representing quantities flexibly. And additionally, working with equivalent fractions gives students experience seeing the equal sign in relational contexts, which we'll talk about a little more later. So with fraction equivalence, students get experience performing symmetrical operations in order to maintain relationships. For example, to make the equivalent fraction 2/4 from 1/2, students need to multiply both the numerator and denominator of their original fraction, 1/2, by 2 in order to maintain the ratio across the fraction bar, which is analogous to the symmetrical operations that they need to do later across the equal sign to maintain equivalence. So we know that we need to maintain this 1-to-1 ratio across the equal sign when we simplify or manipulate algebraic equations. If we're looking at our example here, if we're working with the equation 1/2 times the quantity of y plus 5 is equal to 2y, if we wanted to simplify this equation, we could multiply both the left and right sides of the equation by 2 to maintain the equivalence and get the new simpler equation y plus 5 is equal to 4y. The second connection we see between fraction equivalence and algebra is through experience with flexible representation of quantity. With fraction equivalence, students get very direct experience representing quantities flexibly. The essence of fraction equivalence is finding multiple ways to represent a quantity. Students also get experience thinking about what representations of quantity are most useful in a given context. For example, when trying to add the fractions 1/2 and 4/6, there are many ways students could re-represent both fractions. However, the most useful here would be to only re-represent 1/2 as 3/6 because that quickly brings them closer to accomplishing their goal of adding the fractions. Emerson, Levi, and Carpenter have a really great discussion of how this kind of thinking about fractions relates to algebra. And in algebra, representing quantities flexibly may lead to strategy insights. For example, if students are feeling stuck when seeing an equation like 3y plus 6 is equal to 36, re-representing one or both sides of the equation might lead them to new ideas about how to solve the equation, or lead them to be more accepting of alternate ways of solving problems. And prior work has found that flexibility in strategy use and endorsements, often discussed as procedural flexibility, is important for algebra proficiency and general math proficiency more broadly. So it's quite well established that understanding the equal sign as a relational rather than operational symbol is important for algebra. With fraction equivalence, students get experience seeing this equal sign in relational contexts, rather than just the operationally interpreted equal sign that's often seen in arithmetic contexts. In these fraction equivalence contexts, students might start to see things like 1/2 is equal to 2/4, which is equal to 3/6, where it's clear that the equal sign doesn't mean that they need to perform an operation and put the answer after it, but instead that the equal sign is denoting a sameness or a one-to-one relationship. Seeing the equal sign in this relational way gives the opportunity to disrupt the conception of the equal sign as an operational symbol and might push students toward realizing a relational understanding of the equal sign. So this brings us to our research questions. Our primary research question is whether experience with fraction equivalence affects algebra proficiency. And we expect that experience with our fraction equivalence lesson will lead to better algebra proficiency. And specifically, we're measuring maintenance of equality in problem solving and strategy flexibility. And we also have a secondary question of whether fraction equivalence affects understanding of the equal sign. And we would expect that experience with our fraction equivalence lesson will lead to more relational understanding of the equal sign. As an overview of our method, we're using a pre-test manipulation post-test design during a 1-hour virtual session over Zoom. And we're working with 7th and 8th graders. And most of them have not had algebra classes, but they do have some familiarity working with variables. And we plan to work with 120 students. We have 3 conditions, which I'll talk about next, but that would leave us with 40 kids per condition. So we have 3 manipulation conditions. We have a control condition, which is a fraction magnitude comparison task that I'll talk about a little later. We also have our main experimental condition, which receives only a fraction equivalence lesson. And we also have a third condition that receives both a fraction equivalence lesson and an algebra lesson. This third condition was included as an important check of whether we can improve algebra proficiency in this time frame, even when we directly try to teach it. It may also lead to future studies about what kinds of connections between fraction equivalence and algebra are important, if any, for this condition's success. Okay, so we have a fraction magnitude comparison task as our control. And in this task, students see two fractions on the screen and press keys to indicate which is larger. The task is timed and they're encouraged to respond as quickly as possible. We chose this as our control task because it involves exposure to fractions, but we think it's pretty unlikely that students are using equivalent fractions when doing this task. And we're grateful to Ray Meng for allowing us to adapt our code for this purpose. So our fraction equivalence lesson, this gives experience making equivalent fractions in isolation. So for example, what are 3 fractions that are equivalent to 4/6 or something like that. The lesson that we give talks about maintaining relationships and ratios between the numerator and denominator. It talks about doing the same thing to both the numerator and denominator, and it stresses that across the equal sign, the value of the fractions are the same, even though the numbers look different. We also give experience making equivalent fractions in arithmetic problem contexts, and we explicitly ask them to use equivalent fractions to rewrite the equation to make it easier to solve. And then in our algebra lesson, it gives experience re-expressing quantities and explicitly connects this to the lesson on equivalent fractions. And it also gives experience maintaining equivalence when equations are transformed. And again, this makes explicit connections to what was just taught in the fraction equivalence lesson. Notably, it doesn't teach them how to solve systems of equations or solve for y. So as a refresher then, our 3 conditions are our control fraction magnitude condition, our fraction equivalence lesson only condition, and our third condition, which had both the fraction equivalence lesson and the algebra condition. So we tested several concepts, maintenance of equality, procedural flexibility, and understanding of the equal sign. And all of those concepts had both self-produced and endorsement portions. And then we also just checked their fraction equivalence knowledge, both at pretest and post-test. So for potential results, we could generally find that those who receive a fraction equivalence lesson outperform those in the control condition, which would support our hypothesis that fraction equivalence experience is beneficial for algebra proficiency. And we would probably still expect to see benefits of the algebra lesson. And future studies could untangle whether the fraction equivalence section of this condition was important or not. We could also find that those in the fraction equivalence plus algebra lesson condition outperformed the other conditions, but that there was no difference between our control and fraction equivalence lesson conditions. This would not support our hypothesis, as fraction equivalence experience alone wasn't transferring to improved performance on our measures of interest. And again, future studies could look at whether the fraction equivalence component of the algebra condition and the algebra lesson was important for this condition's success. We could also find no differences overall. And this would tell us that our manipulations weren't powerful enough, and it was too difficult to improve the students' understanding of the equal sign, maintenance of equality, and procedural flexibility in this very short time frame with this kind of manipulation. So as far as implications go, we hope to learn more about whether experience with fraction equivalence affects algebra proficiency, and whether fraction equivalence affects understanding of the equal sign. And as we move forward and go into further studies kind of in this vein, we're very interested in learning whether fraction equivalence can be used to scaffold algebra concepts in the classroom, how explicitly connections between fractions equivalence and algebra need to be made, and how we can best support students making these connections. And thank you to the many people who have given input on this study as we've been forming it. And I'm open to any questions.
Awesome, thanks, Tori. Do we have any questions? I think we have time for at least one. Yeah, Julie.
I'm going to ask probably what everybody is thinking, which you probably hoped nobody would ask, but I'm asking anyway. What are you seeing? Anecdotally, what are you noticing whenever you're working with these kids on these Zoom lessons? Are you seeing any patterns? Are you seeing any aha moments that would lead you to expect one pattern of results more than another?
Yes, so we've give you a couple answers here. The first is that we've been revising our measures because we happen to have a sample that is much farther above grade level than we would expect with these skills. So we've been trying to figure out like what age is actually appropriate to do this with, given the sample that we have. And we've also been revising our measures so we can dig in a little deeper to see, okay, which strategies are kids now endorsing after they've had these fraction equivalence lessons or algebra lessons. So we're very much in flux in that sense, but I think we've got it now, and we're collecting, and I'm excited. But what it looks like so far is we've had a lot of kids at ceiling, so we don't actually have like a lot of data to work from. So far, I haven't noticed like really clear impacts of the fraction equivalence lesson only, but we have seen some changes from the lesson that has both the fraction equivalence and the algebra. So we'll see once we have, with our refined measures and as we get more students, what plays out.
Good luck.
Thank you.
Exciting.
Awesome. Thank you, Tori. Okay, so I'm going to share my screen, and hopefully we'll have time for last couple of questions at the end. So hopefully you can see that correctly. So thanks everybody for coming to our symposium. I've really enjoyed these talks. Thanks to all of our speakers. So I'm Alex Viegut, and I'd like to continue thinking about this connection between fractions and algebra by trying to bring in some insights from math education research. And I am in the Department of Educational Psychology, so I'm trained as a psychologist, but I've been thinking a lot about this connection and reading a lot of math ed work. So I would like to move you guys. There we go. Okay. So today we've heard about how previous research has shown this fractions to algebra connection. And as I've been thinking about this connection over the past year or so, I really think that there are some fundamental questions that we're still really at the beginning of being able to answer. So why does fractions knowledge really help with algebra? Which aspects of fractions and algebra are related? And is this really a causal relation? Does it really only go in one direction? And I think that the three talks that we heard today start giving some really great answers, or at least hypotheses about some of these questions. But I think there's a lot more work to be done to unpack this connection. And as I mentioned, I'm trained as a psychologist. So when I was starting to dive into these questions, I was drawing mostly from evidence of studies in psychology that fractions predicted algebra both at the same time and longitudinally. And then one of the things that I learned as I was reading more is that there's this huge body of research from math education about fractions, and that these folks have also found this connection between fractions and algebra, but using really different methods and measures. So psych research on the fractions algebra connection is usually quantitative with lots of control measures, trying to isolate this causal impact often. And usually we're using pretty brief, pretty standardized measures. And math ed research on this question has taken a really different approach. So they have kind of carefully thought about these mathematical constructs and the mathematical connections between fractions and algebra, and also gotten some really in-depth data with kids explaining their thinking, and shown that fraction reasoning is really related to algebraic reasoning or thinking. And specifically, I'll talk about a couple of the findings here, but I think that, so we've got both of these fields kind of separately showing that fractions are important for algebra, but we're so far working on pretty parallel tracks. And so I think that it would really benefit both of our fields and really our understanding of this question to draw from the strengths of both research traditions. As I am trained as a psychologist, I want to say, what can psychologists learn from math education research on this question? So first, I think that by drawing from some of the ways that math ed researchers have measured components of fractions and algebra, we can think about more comprehensively measuring which aspects of fractions and which aspects of algebra. So instead of just having a general like fractions support algebra, we can start to build more nuanced models of which specific aspects are connected. And then second, I think that math ed research suggests that we should really carefully think about how we define fractions and algebra knowledge and what the boundaries of these constructs are. And I think that might lead us to consider the question of whether fractions could be considered part of algebra as well. So to start, I want to talk about this first point here. So there have definitely been some attempts to get more specific with the fractions algebra relation, including the three talks that we've heard today. And I think that a close latest look at math education research suggests that we could get even more information about this by reaching outside of kind of the dominant measures from psychology. So the way that we typically measure fractions knowledge in psychology, especially with this question of fractions algebra connection, is by using measures of magnitude, like magnitude comparison and number line estimation, and arithmetic like these, like we saw today. But we can also think about measuring fractions knowledge by asking kids to reason about situations like sharing 3 sandwiches among 5 people, or making sense of fraction multiplication through drawing. And these are the kinds of measures that are more common in studies of fractions knowledge from math ed. And on the surface, they seem to be capturing a really different part of fractions knowledge than the more standard psychology tasks. But it's pretty hard to know exactly how these tasks relate, because they're not often given to the same kids at the same time. Math ed research suggests that this kind of fraction thinking is really critical for algebra thinking. And specifically, Amy Hackenberg and her colleagues have done a lot of this work and have shown that disembedding and other fractions operations or mental actions are really important for the way that students reason about and symbolize algebraic relations. Ooh, my light just went out because I didn't move. Okay, so you might measure some of these operations by asking a child something like this. So to draw a piece of pie that's 4/5 as big as the piece shown here. And to solve this, a child can partition or segment the pie into 5 equal pieces, and then mentally pull out or disembed a 1/5 piece. And then they can iterate that piece 4 times to make a 4/5 piece. And Hackenberg has some work interviewing kids and showing that these kinds of operations are really helpful for thinking about algebraic equations, especially those with multiplicative relations like y equals 5x. And another skill that math ed research has shown is related to algebra equation writing that hasn't been used much, if at all, by psychologists is units coordination. So here's an example of units coordination. So you can think of 6 as 3 2s, each of which contain 2 1s. And for us as adults, this seems pretty obvious. It's pretty easy to flexibly think about 6 as 3 2s or 2 3s or 6 1s, but for kids, keeping track of these structures and using them flexibly can be really tough, especially for fractions. So here's another example of the same thing using fractions, that 1 contains 3 1/3 and 6 1/6. This kind of units coordination, keeping track of these structures, is pretty important for algebraic symbolization, especially Hackenberg has found with identifying multiplicative relations between unknowns. So I want to suggest that it's important for us to consider and attend to student thinking in our attempts to answer this, why are fractions connected to algebra? And I think that's important first because I think that dominant measures from psychology might gloss over some important individual differences between students. So we might see that 2 students can place the fraction on the exact same spot on the number line and get the same score, but have really different underlying strategies and ways of thinking about fractions. And this math ed research that I've reviewed a little bit suggests that these differences might have a really big impact on students' algebraic thinking. So I think attending to student thinking in fractions is important. And I also think math ed research suggests that attending to student thinking in algebra is really important as we try to unpack this connection. So most of our assessments in algebra, in psychology, especially in this research on this connection, start by thinking about what is measured in Algebra 1 classes and textbooks and tests. And this is really important. This leads us to ask questions like, how do you solve or simplify equations, to evaluate expressions, and to identify important features of symbolic algebraic notation. And these things are really important for how kids are going to perform in their algebra classes and do in school. But I think that these tasks that tend to focus on algebra performance might miss some of these differences in algebraic thinking. So just a couple examples to illustrate that. here's an example of the kind of algebraic thinking that math ed research suggests is supported by fractions reasoning. So we might show students a pattern and then ask them to reason about the structure of this pattern and symbolize those relations and really justify their explanations. And this is not altogether different than the types of measures we use in psych, but it does focus much more on this algebraic thinking. Another example is this. So a friend gives you some money. Can you tell which is larger, that amount of money plus $6 or 3 times that money? And kind of explain your answer here. This is another task where it's really trying to get kids to explain their thinking and justify their answers. And tasks like this are pretty uncommon in psych studies, especially in these studies of the fractions algebra relation. So I want to kind of wrap up by saying that fractions are likely important for algebra in multiple ways. So it's possible that these two separate bodies of research are capturing the same relation between fractions and algebra, even though we're using different measures. But I think it might be more likely that we're capturing kind of unique paths or mechanisms, that psychology might be capturing one reason why some parts of fraction knowledge are related to some parts of algebra knowledge, and math ed might be capturing kind of a different mechanism or reason why fractions and algebra might be connected. But it's hard to know because we, again, haven't really been using the same measures with the same kids. And so I think we should consider combining both types of measures with the same kids at the same time. And then lastly, let's see, in my last minute or so, I just want to leave you with one more question to keep thinking about. So where are the boundaries between these categories? So fractions and algebra are huge mathematical ideas. These types of knowledge are just really broad constructs, and they're long developing over time. And so where are their boundaries? So the way that we tend to talk about it, and the way that I've tended to think about it, is that there's this kind of causal relation that we're trying to unpack. Why and how do fractions help us with algebra? And I think a lot of the longitudinal evidence that we've seen today and in previous research supports this kind of causal pathway. But kind of an alternative way to interpret some of that might be to think about fraction knowledge as being part of this broader algebra knowledge construct. And I think that the work that Tori J presented kind of starts to suggest this, that fractions are really all about helping kids to practice with generalizing mathematical relationships. And that's all what algebra is all about, right? So it's possible that fractions might be considered part of algebra, or at least that there are ways to teach fractions that might emphasize their algebraic character. So with that, I just want to say thanks to a lot of folks who've been helping me think about these questions, especially to my dissertation committee here and to the folks in my lab and to all the people who funded me throughout my time in grad school. So I will stop there, and I believe we have a couple of minutes for anyone who's got questions for me or for any of our speakers in the last couple of minutes.
So I'm happy to ask a question if no one else does, but if someone who doesn't get to see Alex as often would rather ask a question, I'm willing to let someone else go ahead. I guess, Alex, in the spirit, then hearing no one, Alex, in the spirit of your efforts to bring together perspectives, do you think that the two perspectives that you identify might also be able to be unified? Like the idea that there's a causal mediator or that there's a constitutive part, that maybe that those are kind of potentially sequential processes, or that they might come together in some way?
Yeah, I mean, I think that you could consider those together. I don't think they're mutually exclusive. I do think they're a pretty different kind of way of theorizing about the relation, and definitely, yeah, like kind of a different way of framing it. But it's certainly, you could think about fractions as sort of like early algebra skills, right? Or as part of early algebra skills. And then that causal relation could still be consistent with that, right? Yeah. I think that's reasonable.
I mean, you might think you might learn them first in an isolated way and then
Sure.
link them to other ways of reasoning and generalizing with numbers that might then become this constitutive kind of.
Yeah, sure. All right, well, I want to be respectful of everyone's time. So we are at an hour. So I really want to say thanks again to all of our great speakers. This was a lovely series of talks, and thanks to all of you for coming. And I'm happy to stick around if there are a couple more questions, but otherwise, thanks so much and have a good evening or a good day wherever you're at.
Thank you, everyone.